What I would like to do, as I said last time, we are going to be doing lots of little set theory arguments, and I wanted to make sure that everybody is still feeling good about writing set theory proofs, which you may not have written proofs like this since you were in a discrete math class. So I thought it'd be a good little review. I thought maybe we could do one all together, and then I have a few for you to try. These are, I mean, if you know what you're doing, these are simple set theory type proofs. Set theory is what I want to talk about. Just a little review, if you will. How about let's prove this A union B intersect C. There's sort of like a distributive rule for unions and intersections. This is the same as A intersect C union B intersect C. All right, this is a distributive type property for unions and intersections. Can we demonstrate this? Now, I have two sets, and I need to show that they are equal. The standard way to do that is by showing that one is a subset of the other one, and then the other one is a subset of the first one. And to do those, you typically take an element in one set, and then show that it's also in the other set. And then you take an element in the second set and show that it's also in the first set. So that's going to be my strategy here. So I'm going to, I'll just write that out. So we'll show that A union B intersect C is a subset of the other thing. A intersect C, union B intersect C. And then also the other thing is a subset of the first thing. So A intersect C, union B intersect C is a subset of A union B intersect C, like that. All right. I'm going to show the one is a subset of the other, and also the other is a subset of the one. If you're lucky, both of those parts will look pretty much the same. Sometimes you can make it so that you basically write the same thing both times. Sometimes it's more complicated than that. So to do the first part, let's do the first part first. So I'm going to say first, the way you prove one of these subset things is you choose an element in the first set. So I'm going to take, let's say, X, an element of A union B intersect C. And then I'm going to show this. I will often write this WTS, means want to show. I'm going to show that X is in the other set. That is, X is in A intersect C union B intersect C. All right. And for this one and for the other ones that I'm going to ask you to do, you don't really have to think all that much. You just have to sort of write down what it means that X is in that thing. So I'm going to say, since X is in A union B intersect C, first of all, I will handle the intersection. The intersection means like and, right? If X is in this intersection, it means X is in the first thing and also X is in the second thing. So that means X is in A union B and X is in C, right? That's what intersection means. Okay? So that means, can I write again what this means? We can sort of expand out what the union there means. A union B, that means that X is in A or X is in B. All right, so I'll say that. X is in A or X is in B. I'll sort of put that in parentheses. And also X is in C, right? If you like, you can write, some people write like ors and ands with little wedges and pointy things. That's fine if you want to do that. I'm usually just going to write ors and ands. All right. Can we rewrite this in some way? I'm going to try to somehow get there. I want to arrive at this point, right? So I'm going to sort of refactor this or kind of distribute ors and ands. This says X is in A or X is in B and also X is in C. That's the same as X is in A and X is in C, or X is in B and X is in C, right? It is a fact. because the previous line said that X is definitely in C, and it's either in A or B. And then what I wrote here is just kind of breaking that into 2 steps. It's either in A and it's in C, or it's in B and it's in C. All right? But now I can just sort of change all these ands and ors back into unions and intersections. So the fact that I have A and C here, that means, so X is in A intersect C, or X is in B intersect C. And that or turns into a union. So X is in A intersect C union B intersect C as desired, right? So that is half of this set theory proof. I hope you kind of agree that this doesn't require a whole lot of thought to it. It's just a matter of looking through the definitions of intersections and unions. All right. Anybody got questions about that? Really, this is only half I should do. The other direction would start here and end up going back to here. Now, in this example, actually, you could just write the whole thing in reverse, and all of these steps would work in reverse because all I used every time were just definitions of intersections and unions. So if you like to, you could just write the whole thing in reverse, or if you're feeling very confident, you could just say the whole thing works in reverse too. Although that's a flex move, really. You are very, very confident in your approach, which is fine with me if you want to write that. Let's try and actually write this out. I'm gonna do the other direction. I'm not gonna just write the same stuff again, just because that's kind of boring to me. Let's see if we can do this kind of from scratch. So the second part, I'm gonna say, I'm gonna start off like I did before. Take X in. This time it has to be in the other thing. Intersect C union B intersect C. And then I want to show that X is in A union B intersect C, right? This is the other direction. So maybe I thought just for the sake of variety, I would write this proof a little bit differently. I'm going to say, oops. Since X is in the union of those things, A intersects C, union B intersects C, this means X is in A intersects C, or X is in B intersects C, right? Now, if I assume an or, it's a typical thing to write the proof in 2 separate cases, right? Either it's in A intersects C or it's in B intersects C. And I can handle those as 2 separate cases. So I'm going to break this into cases. I'll say case 1, if X is in A intersects C. In that case, remember what I want to show is that X is in A union B intersects C. But actually, if you think about the way that unions work, A intersects C is just like a smaller set than A union B. This one is just bigger. It has all the stuff in A intersects C, but it also has some stuff from B, right? So I'm going to say it this way, then A intersects C. Would you agree this is actually a subset of A union B intersects C? That's because all I did there was insert some more stuff, maybe, by unioning with B, right? The thing on the right there has just strictly more stuff than the thing on the left. And so, if X is in A intersects C, then X is in A union B intersects C, which is what we wanted to show, right? I said I wanted to show this. X is in A union B intersects C. All right, so that was the first case when X was in A intersects C, but the other case is basically the same. So the other case was X in B intersects C. So case 2, if X is in B intersects C, I'm going to say basically the same stuff. B intersects C is also a subset of A union B intersects C, because the only difference there is you throw in some extra stuff, the stuff which is in A. All right, so if X is in B intersects C, then X is in A union B intersect C. And that's really the end. Shun. Shun is what I like to write at the end of a proof. I think it's a great thing. All right, this is the complete proof. Anybody got questions about this? This is a nice little review for the comprehensive exam if you're into that. This would be a typical discrete math comprehensive exam question. I'm not saying this is on the exam. I'm doing this for the sake of our course. Any thoughts? All right, I got a few more sort of in this general on this general theme here that I would like for you all to try. So this is another similar looking sort of distributive-like property. It says x minus A union B. This is the same as x minus A intersect x minus B. Remember, the minus means it's like a complement. This means all the things which are in X, but they are not in A union B. All right? And this over here. This is actually one of the De Morgan's laws for complements of a set. This says the complement of A union B is the complement of A intersect with the complement of B. In some discrete math class, maybe you wrote complement with a prime or with a little C or something. In our textbook, they don't have any special notation for the complement. They just always write it with the X minus or whatever. Okay, I got just a couple more here. We are often going to be working with functions, so try that one, and then also try this one. This is about the pre-image of a function. I hope you remember what that little F inverse of a set means. All right. Now, each of these is about one set equals another, if you like, and they really require two separate arguments. You choose an element in one and show it's in the other, and then you do the other way around also. If you like, just for the sake of time, I don't want to spend all day doing these. If you like, you could just try one direction of each one of them if you want to simplify things. In all of these cases, the same argument basically works both ways around. All right, see what you think. I will give you a few moments. I'm going to walk around and see how you're doing. I hope you don't mind me asking how you're doing. I'm not trying to, give you a grade or anything like that. I'm just trying to be helpful if I can. I'm also going to try to turn this screen on. I hope it doesn't ruin everything. Right now, these buttons claim that everything is off. Just turned it on. Ooh, something's happening. Ooh. Yes. Huh? Oh, yeah. I did nothing different, but it worked this time. feel free to talk to your friends, talk to the other Julias. I was kind of hoping all the Julias would sit together as a unified front, but it's all right. You don't have to. Yeah, 3 out of 4. I don't want you to feel left out. The kind that's rejected you. Try. We used to have 3 Chris's in the math department faculty. It was a strong coalition. We're down to 2 now. Good? Mm-hmm.
I was deciding whether or not I want to go back to the other night or just try this one.
Yeah, I would suggest try to do like half of each one, just so that you get a little flavor for everything. I hope you remember what F of A union B means. That first one, all right? Mm-hmm. Okay. I'm going to try to write out what I would have written for the first one, just because it seems like most people are doing all right. I think maybe the third one might actually be better, easier than the second one. I don't know if you feel that way. Is one all right? Take X here. I would say the next thing to say would be, what that means is actually X is an answer that you get out of here. Actually, I might more comfortably call that Y. It means there is some X. How's it going? Maybe we could talk about the just how to get started on the second one. The second one, this F of a set is a little weird. I would begin the second one, so you'd say, take X in F of A union B. Actually, for reasons which may become clear, I'm going to call this Y rather than X. What it means is Y is one of the answers you get out of the function if you start with the domain of A union B. So if Y is one of these answers, so what that means is there exists X in A union B with F of X equals Y. That's what that means. There is some point from A union B which becomes Y when you do F to it. And then see if you can monkey around with this business to show eventually what you want is to show that Y is in F of A union F of B. That is to say, there's some point from A which becomes Y, or there's some point from B which becomes Y. That's the idea. So you want to sort of break up this is x is in A, and that means either x is in A, or this is A, or x is in A, so A or it's all right. Remember what that means? It means when you do f to x, the answer is in A. Did you get the previous one out? How's it going? I would say maybe it's a little, you know, hard to say. Yeah, something like that. So either x is in A and x is in Y, or alright. Yeah. How'd it go?
Do you think I should break this down one more time before going here?
Oh, yeah.
No, this is
Yeah, I should just write this there and just like that.
alright. Yeah, I think it might be a little break. So something like, because we'll assume this, right? This is true, right? So maybe say x is in A and that's true, or x is in B and that's true. Becomes a little clearer.
So is this sufficient enough to say, or is there something to break down even more from this?
Well, I think you can say like that means y is in f of a.
Okay, and then this means that y is in f.
Right.
So, and then it's the whole.
Yeah. Yeah.
That's good.
Alright. All right. It looks like folks are doing good. Can we go over these? I know as I'm going around, I saw nobody is actually done, but I just want to keep it moving for today. So maybe I will write in, as I was walking around, it looked like people were doing pretty well here. I would say, of course, there are many ways you can write this, but I would say something like this. I'm going to break up the union. Either x is in A or x is in B, and in either case, f of x equal y. So I'm going to say, so x is in A and f of x equal y, or x is in B and f of x equal y. And then each of those, I can say, so the first one here, this means y is in f of A, right? That means there's some point x from A, which f of x equal y. And then the other one, or y is in f of B. And finally, I write this as a union. So y is in f of A union f of B. The end, right? That's what I wanted, or at least the end of half of the proof. All right. as I was looking around, it looked like pretty much everybody came up with something like this. I hope that you did. Anybody got questions about that? All right, let's try the third one. Was about the pre-image. This is actually a true fact that I don't know if you got to experience this much. My experience teaching discrete math, I don't typically talk a lot about the pre-image, but actually in this class we're going to talk about the pre-image fairly often. And it looks kind of complicated on paper, but actually in general the pre-image is easier to work with than the ordinary image of the function. So I'm going to do similarly. I take x to be in the pre-image. I'm calling it x rather than, I called the previous one y because it was like something you get as the answer out of the function. But actually this one, it really should be something in the domain because that's what the pre-image, it's the things in the domain. What it means is, can anybody say, what does that mean? Like the definition of the pre-image of that set? There's a simple way to translate that into a nice little something. X is what you get when you start with things in A union B and sort of bring them back with the function. The other more useful way to say that is if I do the function to x, what can you say about if I apply the function to this x? What can you say about that? Yeah?
There exists a y, A union B.
Yeah, actually it equals something in A union B, right? Yeah. So actually the way to say this is f of x is in A union B. This is why the pre-image is easier to deal with than the ordinary image, because the ordinary image, you had to break this into a thing about there exists one thing with something else, but actually it's a lot simpler to make sense of what the pre-image is, provided you remember what the pre-image means. But this is what it means. When I say x is in the pre-image of a set, it means f of x is in that set. All right? Okay, and now what? Well, now I'm going to break this down into saying some stuff with ors, right? So that means that f of x is in A or f of x is in B. Anybody see where I'm going with this? Could we rewrite f of x is in A in some way? Eventually I'm trying to end up with f inverse of A union f inverse of B, right? That's what I want to get to. But actually I feel like I've got the or here, so yeah.
Could you do f inverse of A equals x or f inverse of B equals x?
Yeah, so the proper way to write this is that f of x is in A is the same as saying x is in the pre-image of A. And then this one, f of x is in B, is the same as x is in the pre-image of B with an or in between. And then that immediately means the thing at the end. So x is in that union. All right, the pre-image. It's a little confusing, but once you, if you are correctly handling the pre-image, usually it actually is nicer than the ordinary image because you can, what the pre-image means you can write in one single sentence or one single statement with no, there exists something or other with some other variable name or whatever. It works out nicely in general. All right. In this class, like in topology in general, you talk about the pre-image more often than the ordinary image. All right. Here ends the little review of set theory. I hope that you feel more or less comfortable about these. Do you think it would be helpful if some of the first homework assignment was like just sort of set theory review kind of things? Maybe I'll put a couple of questions of this nature on the first assignment. Another thing which will become important, which I didn't give an example of right now, is the product of two sets. I hope that you remember something about the Cartesian products, but maybe that's for the homework. All right. I want to actually talk about some topology today. So let's talk about topologies. Topology is actually a noun. Like, we are going to talk today about a topology. Like, you can have this topology or you can have that topology. How many topologies do you know? You can ask your friends at lunch. I know of several different topologies. There are different topologies. Anyway, point set topology is what this class is all about. And like I said before, it's kind of about shapes, but not really about geometry, all right? What is important in topology is not exactly the geometric structure of a set, but it's really more like, what are the points and how are the points connected with one another? Another way of talking about that is point set topology is about, I will say, connections and maybe nearness. It makes sense to talk about what are the nearby points to this other point in a way which I don't really care about the specific distance, but I do kind of care about which points are close to one another, which points are connected to one another, which points are disconnected from one another. And so the basic concept of nearness is, I'm going to say we discuss this via open sets in real analysis, and even in like calculus. You know the difference between an open interval and a closed interval. In real analysis, you learned about, like, actually there is a related but a little bit more general concept of an open set in general and a closed set. An open set you should think of as a set which doesn't include its boundary points. That's kind of what an open set means. Really, more technically, in the real line, an open set is a set so that around every point of the set there is a epsilon neighborhood which is contained inside the set. That's the definition of open set from real analysis. But we don't want to fixate on that particular definition, but I will just say in R, an open set, let's just say U subset of R, means, well, what it means is, I'm just going to write some nonsense here, but this is what it means. It means for all points in U, there exists some epsilon greater than 0 such that the epsilon neighborhood around X, which is to say the interval X minus epsilon to X plus epsilon, is a subset of U, all right? That's a complicated definition which just looks like a bunch of nonsense if you don't know any real analysis. And we're not really going to fixate on this all that much. You did plenty of that in real analysis with the epsilons and such. But I'm just trying to say, in the real number line, this is the way that open set is defined. It's defined in terms of these epsilon neighborhoods. All right. And in real analysis, you saw theorems about combining open sets together. So this is a theorem from real analysis. It says that I don't know if you remember this. This is actually super important, kind of like foundational to the whole course. Any union of open sets is open. This is a true fact. In R, you can usually think of an open set as being an open interval. And if you take unions of open intervals, that's still an open set. Any union of open sets is open. And also, any finite intersection of open sets is open. These are fundamental properties of open sets in R. And those are two theorems that you should have seen in your real analysis class. I don't know if you remember it, and it doesn't especially matter if you remember how the proofs of those go, but this is basic fact about open sets in R. Any union is open, and any finite intersection. By finite intersection, what I mean is intersection of finitely many sets. Like if I just take three open sets and take their intersection, the result is open. If you take infinitely many open sets, their intersection might not be open. But finitely many, intersection of finitely many sets. I'm not saying that the sets themselves are finite sets, just that there's finitely many sets, all right? When we define open sets in this way, so what we're going to do is, or point set topology, PS topology, is all about different abstract definitions of the concept open set. So in real analysis, open set means that thing about epsilons, but actually in this class, when I say open set, I don't necessarily mean that. I mean something which is a little bit more abstract. This is a little bit like how in your abstract algebra class, you talk about a group is a set with an operation, and usually you call the operation product or multiplication, even though it's usually not actually multiplication like the ordinary multiplication from numbers. It's usually some other kind of operation. But the point of doing studying group theory is like you can prove theorems about groups which will apply to every group, not just ones with ordinary operations, but it could apply to any group with any operations as long as it satisfies the axioms for being a group. And this is the same kind of thing. We have a ordinary concept of open sets from the real numbers. But actually, topological theorems are proved in the context of any kind of setting where there are some sets which are called open sets. Now, just like in algebra, it can't be anything at all. It has to obey certain properties. So we are going to talk about different abstract definitions of what it is to be an open set. But they are required to obey certain properties, just like the group theory axioms, associative, whatever. The properties are totally different in this case because there's no operation. But basically, the properties are going to be this. This is the fundamental property of what it is to be open, that any finite union, or any union at all of open sets is open, and any finite intersection of open sets are open. All right. So topology is really about, I'll just say we'll consider any way of describing open sets as long as the union and intersection properties hold. That is, any union of open sets has to be open, and any finite intersection of open sets has to be open. All right, so I'm going to give you could consider those at kind of like topological axioms, just in the same way as group theory axioms. But I'm going to write this as my official definition here. So I'm going to say let X be any set. You can imagine that X is like R or R2 or something like that, but really it could be anything. And I'm going to also assume, I'm going to say let T, this is my fancy looking T. I hope you have a fancy font in your hand. This fancy looking T, let this be a collection of subsets that are going to be called the open sets. You can imagine them as being like open intervals inside of R or something, but they might not look anything like that. So they are just some subsets which we declare to be open sets. Then we say T is a topology on X. A topology on X means this is like a legal description of open sets versus not open sets. T is a topology on X when these properties are satisfied. There are three of them actually. One is about finite intersections, one is about unions, and then there's sort of this other one for free. Property number one is X is in T and the empty set is in T. All right. T is the collection of sets which I call open. So what the first property says is that the entire set is always considered to be open, and the empty set always counts as open. So another way of writing this in more informal language is just X and empty set are open, right? When I say they are in T, what I mean is, T is just a big list of all the open sets. So another way of saying that is that X and the empty set are open. All right, that's the first thing. The second thing is about finite intersections. Any finite intersection of sets in T is a set in T, right? This is the finite intersections property. And then the third one is the unions property. Any union, finite or not, of sets in T is a set in T. All right? If those three properties are true, then you can do topology with this description of open sets. All right? Like I said, you should think of these as similar to the basic axioms which are required in group theory, or even like, I don't know if you remember in linear algebra, at some point, you probably didn't like this, but they started talking about like a vector space is any kind of thing which satisfies these 10 properties or something like that. This is a very common way of presenting basic ideas in mathematics. A topology, we think of it as being kind of like R and open intervals in R, but it's not necessarily like that. What is it like? Well, really, the only properties which are necessary are these which I wrote right here. The finite intersections and the unions property. And just that the whole set and the empty set have to be considered to be open. All right? In this case, so I'm going to say if X has some topology T, then these together form what we call a topological space. A topological space. So a topological space means a set which comes together with a topology. That is a description of which are the open sets and which are not open. All right? This is like, what is a group? A group is a set together with an operation that satisfies these properties. A topological space is a set together with a topology, which has to satisfy the three properties. All right? For example, so R using epsilon neighborhoods to define open sets, like I said before, is a topological space. All right? This is referred to as R with the standard topology, because when I just say R in general, you assume that I'm talking about R with those particular open sets, the open intervals and unions of open intervals. So R using the epsilon neighborhoods to define open sets is a topological space. This is called R with the standard topology. Right? And if you use the standard topology in R, then all the theorems you know from real analysis are true. For instance, like R is a connected set. This is true because you're using the standard topology in R. R is not a compact set. Although if you change the topology, then maybe it would become compact or maybe it would become disconnected. All right, this is R with the standard topology. There are other non-standard topologies on R, though, that you can make that we will talk about eventually. In our remaining 3 minutes, there's actually, so I want to give you some example of something which is not the standard topology on R. And we're going to do some more interesting examples next time, but for today I will give you 2 stupid examples of a topological space. So these are two, I will say, trivial type examples. Maybe I'll just say stupid examples. Of topologies. First of all, for any set X, remember the rules for what makes a topology is it has to, first of all, X and the empty set always have to be open sets, and then the stuff about unions and intersections also has to be true. For any set X, I can let T be empty set comma X. That is, you can consider that there are no open sets at all except for the empty set in X. That they have to be open sets according to the definition of a topology, but maybe those are the only open sets. All right, this is a topology because certainly it satisfies the first property, which is that X and the empty set have to be they have to be open. And then it also satisfies the unions and intersections property, because you have to just think about, what if I take a union of these two things? Is the result still one of these things? Well, empty set union X is equal to X, which is one of these things. So it does satisfy the unions property. What about the intersections? Empty set intersect X is empty set, which is also one of these things. So it does satisfy all three of the properties. This is like the smallest possible topology that you could use on any set. All right. This has a name. This is called the trivial topology. We will almost never talk about this topology because it doesn't lead to anything interesting about your topological structure. All right. The trivial topology is one in which basically no set is open, apart from the empty set and the whole set, which are requirements. All right. Anyone want to suggest another there's a stupid example kind of the other way around. This is one in which no sets are open. Can anyone think of a kind of an opposite or converse like thing? I'm thinking about some kind of all or nothing. This is nothing, where no sets are open. How about, just because we gotta go, how about you could make it so that every set is open, right? And then does the union and intersection property hold? Well, if all sets are declared to be open and you take a union of two of them, then the answer will still be open, right? Because you're just saying up front that all the sets are open. So this is the trivial topology. Also, these are the two stupid examples. You can make it so that no sets are open, or you can make it so that all the sets are open. Neither of those examples is very interesting, but they are both technically legal topology. So also I can say for any X, let T be, actually, the set of all the subsets. You could write it this way. The power set of X, all subsets are open, right? All subsets of X. And this also is a topology, which is similarly uninteresting, sort of for the opposite reason. The first one was uninteresting because there are no open sets. The second one is uninteresting because everything is an open set, and then there's really nothing interesting to say about the open sets because they're all open. So this is a topology too. This is called, this has a more interesting name, the discrete topology. And we will eventually, it's not really obvious why to use that word, but we will eventually talk about why that word is used for this. The discrete topology. All right? Those are two sort of stupid ones. We're going to talk about more interesting ones next time. Thank you for your